Thank you.
Okay, so the quiz is going to be on Friday. Except we don't have school, so it's on Thursday.
What? What's on Thursday?
The quiz. Oh, first quiz.
Wait, but you can't. You have to take off one homework then. Because it was getting on Friday.
Okay, number 4. Come on! Al, Ben, Cal, Dan, and Ed. You're going to randomly select 3. So one way to do it is just write out the sample space. What can happen when you select 3 people? A, B, C, A, B, B, A, B, E, A, C, D, A, C, E, A, D, E, B, C, D, B, C, E, B, D, E, C, D, E. So how many elements in the sample space?
10.
So you know the answer is going to be something out of 10, and then you just answer the question. What's the probability that Cal is on the committee? Well, look for all the ones that have Cal. 1, 2, 3, 4, 5, 6. 6 out of 10. If you can write out the sample space, the problem is done already. What's the probability that Al and Dan are on the committee? So where do I find Al and Dan? Right there. 1, 2, 3. 3 out of 10. But did you guys do the problem using combinatorics though?
Yeah.
So if you're going to use combinatorics, then the denominator would be
5.
5 choose 3. And which one you want to do? Let's do B. If Al and Dan are on the committee, that means Al and Dan are on the committee already. You only have to select one more person. So of the remaining 3 people, how many ways can you select one? 3, choose 1, and that's the way you would do it using combinatorics then, yeah?
Wait, which one is that?
B. Okay, what about E, C? Ben, Cal, and Ed are on the committee. Yeah, so there's only one time they're going to be on the, so it's going to be 1 out of 10, right? Okay, number 5. Well, first of all, you got to understand the problem. Period 4 didn't even understand. Period 3, they didn't even ask. What is the probability that this expression, 3x squared minus 4x minus k, can be written as a product of 2 linear factors, each with integral coefficients? Now, what the heck does that mean? That means you can factor it. So, one way is, okay, you're going to randomly select one number from here. There's 8 numbers, so you know the answer is going to be something out of 8. So what do you want to do? Plug each number in and see if you can factor it? Yeah, you can. But what's a faster way that we learned in the first quarter? You look at the discriminant. And what does the discriminant have to be in order for the thing to be factorable? Perfect square. Okay, if you have a quadratic function, okay, then you use the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. This is called the discriminant. Did you ever use like the quadratic formula and this came out to a perfect square? So when you square root it, you get a rational number. Then you think, oh darn it, I could have factored it. Yeah, that's how you tell if you factored it. It's factorable. This thing is a perfect square. So the discriminant is b squared minus 4ac. We want this to be a perfect square. So what is that? 16 plus 12k. We want that to be a perfect square. So just plug in these numbers one at a time until you get a perfect square. Yeah, you can, but then look, you can even make it even simpler. Factor out of 4, which is a perfect square. You get 4 plus 3k. Because 4 is already a perfect square, so in order for the whole thing to be a perfect square, then just that has to be a perfect square, right? Yeah, so instead of plugging it into this ugly thing here, plug it into that nicer thing there. Now it's easy. If I plug in negative 3 for k, is that a perfect square?
Yeah. No.
4 minus 9 is a perfect square? No. Plug in negative 2. 4 minus 6. Come on, it's a negative number. How can that be a perfect square? Plug in negative 1. 4 minus 3. Height! Plug in 0. Height. Plug in 1. 9. 2.
No.
If I plug in 2, you get 4 plus 6. Is that a perfect square?
No.
Okay, thank you. Plug in 3. 4 plus 9. Plug in 4.
Yep.
Yes, so the answer is 3 out of 8. I guess I know which problem to put on the quiz then, yeah? I don't think we're going to have problems with that one. Okay, number 6. Boo! Okay, I'm going to randomly pick a number between 1 and 999. What's the denominator going to be? How many elements in the sample space? How many, basically, so one way is you can just subtract and add 1, right? Or, how many 3-digit numbers are there? 9, 10, 10, right? 900, either way. Okay, what is the probability that this number contains no 7s? Now, did we do this problem in the last chapter? How many 3-digit numbers contain no 7s? What did we do? 8, 9, 9, because the first, how many choices do you have for the first digit? Anything except the 0 or the 7. So you got 8 choices. How many choices do you have for the second digit?
9.
9, because now you can pick the 0, but you just can't be the 7, right? And same thing for the third digit. So this is the probability that it contains no 7s. So what would be the probability that it contains at least one 7? You subtract it from 1 because it's the complement. You guys understand this idea of complement? What's the, okay, you have a die, I rolled it. What's the probability of rolling a 6? 1 6. So what's the probability of not rolling a 6? Yeah, you subtract it from 1, right? Because it's the complement. And then number 8, this is the one that separates the sheep from the goats. How many people got it? 1, 2, 3. So total 4 people got it there. You 3 plus Vol. Everybody else failed. Okay, well, to do this problem, you have to know a little geometry. Okay, here is square A, B, C, D. Where can I put point X so that angle AXB is an obtuse angle? Well, if you had a semicircle right here, if I were to put point X on the rim of the semicircle, what kind of angle is this right here? 9. It's a right angle. Why, and we talked about this several times this year so far, if you have a semicircle, why is it when you put a triangle in there, it's going to be a right triangle? Okay, let's go back to geometry. What kind of angle is this called again? This is like the 3rd time I drew this picture this year, yeah? This is called an inscribed angle. An inscribed angle is always half of the intercepted arc. If this is 80 degrees, this is 40 degrees. So why is it when you have a semicircle, why is it when I put an angle right there, it's going to be 90? Yeah, because this angle is half of this arc, but since this is a semicircle, it's 180, so therefore that has to be 90. It's going to be half of that. Okay, so we established if you put point X on the rim of the semicircle, you get a perfect 90-degree angle, but that's not the problem we're doing. We want to know what's the probability that the angle will be obtuse, that means bigger than 90. So where do I have to put point X so that you get an angle bigger than 90? Inside the semicircle or outside the semicircle?
Inside.
Inside, right? Because it's, gotta be bigger than 90, right? Because if it's on the rim of the circle, it's equal to 90. So this problem just boils down to, if you randomly pick a point inside the square, what's the probability that it will be inside the semicircle? Well, you just look at area, right? The answer is the area of the semicircle over the area of the square. So, what do you want to call the radius of the circle?
R.
Okay. Another class had 1, which is good, but you guys want to do R? Okay, so what is the area of the semicircle? Pi r squared times 1/2, right? It's half a circle. Divided by the area of the square. Well, if that's r, this is r, so the sine of the square is 2r. Therefore, the area of the whole square is 4r squared. And the r's cancel out. So the answer is multiply top and bottom by 2, pi over 8. So a little bit more than 3/8. I remember last year on the quiz I put what's the probability that the angle is acute, and all hell broke loose. That means the point got to be here, so it would be the area of this one divided by the area of the square. Can you guys handle that? We'll see you on Thursday. Okay, today we go to probability 2. So actually we're taking it quite slow because probability 2 and 3 kind of go together. Okay, now what are the two, if you look at your notes, the two theorems we're going to be using today are this. The probability of event A and event B occurring is equal to the probability of A times the probability of B knowing that A already occurred. That's what this thing means. This is the probability of B knowing that A already happened. Anyway, the main point of this thing is, some of you going, what the heck is that? Is this, when you see the word and, that implies multiplication. The word or implies addition, just like when we did combinatorics last chapter. Now, what would happen if you have two events, but the outcome of this is not affected by this? What do we call these two events? When the outcome of one does not affect the outcome of the other. No. Mutually is exclusive means two events cannot occur at the same time. This is just the outcome of this does not affect the outcome of this. Independent, that's the word. They're a little bit different. So if two events are independent, then the theorem is this. The probability of A and B occurring is simply equal to the probability of A times the probability of B. It's basically the same thing, except that this one you have to take into account what happened when event A occurred. Now, some of you just automatically do it in your head, so you don't even think about it this way. So here, let's just do an example. Let's suppose you have a jar. Here's a jar. In this jar, I have 2 blue marbles, 3 red marbles, and 2 green marbles. Now, what's funny about that? I had to change it to marbles because in period 3, it was balls, and then all hell broke loose. He said balls. Okay, now, do you think you're going to get problems like this in pre-calculus honors? I'm going to randomly select one marble. What's the probability that it's green?
Zero probability of you asking a question on a quiz.
Yeah, that's right. But the answer would be 2 9s, right? That's too simple. We're going to have problems like this. I am going to randomly select, randomly draw would be a better word, 2 marbles. Okay? What is the probability that both are blue? Okay, now when you do probability problems like this, when you're pulling out things one at a time, there's 2 cases you got to think of. One is called with replacement, and the other one is without replacement. Have you heard those terms before? With replacement means you're going to pull out the ball, look at the color, and then throw it back in. That's with replacement. Without replacement means you're going to draw out a ball, look at it, and then keep it up. And then pull out another one. You know what I'm talking about? Now, if I don't say anything, like I don't say with or without replacement, which one do you assume?
Without replacement.
Without replacement, because that's just the normal way, right? Come on, how many times, how many applications can you think of where you look at it and throw it back in? Well, sometimes, right? Okay, so let's do a specific case. So the first way we're going to do it is we're going to do it without replacement, okay? I'm going to draw 2 balls, one after another. What's the probability that both are blue? So do a specific case. What's the probability of getting a blue on the first and then a blue on the second? What's the probability of pulling out a blue on the first draw? 4 9s. Okay, now, once I pull out a blue ball, there's only 8 balls left in the bag now, right? And there's only 3 blue ones. So what's the probability of now pulling out another blue?
3 8.
3 8s. See, that's what this is. What's the probability of pulling out a blue ball on the second draw, knowing that you pulled out a blue ball on the first draw? It affects the outcome of the other. That's what this thing here means. But you really don't even, you just normally think of it, right? I mean, you don't even think about it that way. Now, is that the only way you can get 2 blue marbles? Blue on the first, blue on the second? Or is there another way you can get it? Kojima said there was another way. But he couldn't figure it out. No, that's the only way you can get 2 blue marbles. Blue on the first, blue on the second. That's the answer. And please, when you, okay, so this is 3 out of 4 points, but you're not going to get a problem this easy. Please do not do this when you do the computation. 4 times 3 is 12. 9 times 8 is 72. And then you can reduce that. You guys know how to cancel, right? I have to explain this because every year there's always a few people that do this. They multiply out the top, multiply the bottom, and then reduce. No, it's called canceling, people. 4 goes into 8 2 times. 3 goes into 9 3 times. 1 6. I have to explain that. What's the probability of getting 1 red marble and 1 green marble? Okay, let's do a specific case. Red on the first draw, green on the second draw. What's the probability of pulling out a red marble on the first draw?
1/3.
Okay, let's just go 3 9s. And then what's the probability, now that the red marble is out of the bag, what's the probability of pulling out a green one? 2 8s. But, is that the only way you can get one of each color?
No.
No. There's another order, right? Because since we're pulling out the marbles one at a time, there's an order. So this is just the probability of getting a red on the first draw and a green on the second draw. But we're just asking what's the probability of getting 1 red and 1 green. So how many different orders can you put that in? 2. So you need to multiply by 2. You guys understand? Because when you pull out marbles one at a time, there's an order. Does that make sense? So again, just like combinatorics, you do a specific case and then multiply by the number of cases. And then I think you guys can compute that. Okay, let's kick it up a notch. Now I'm going to randomly draw 3 marbles. What's the probability of getting 1 of each color? Okay, let's do a specific case. Blue on the first draw, red on the second draw, green on the third draw. What's the probability of that happening? 4 9s. Now I have blue one out of the jar. 3 8s, and then 2 7s. See, most people can do that, but then now, is that the only order you can get 1 of each color? No, so how many different orders are there here? So you need to multiply by 6, or 3 factorial, right? It's like, how many ways can you arrange 3 things in a row? 3 factorial, which is 6. And then let the canceling begin. What's the probability, now same thing, draw 3 marbles. What's the probability of getting 2 red and 1 green? Okay, let's do a specific case. Red on the first, red on the second, green on the third. What's the probability of pulling out a red marble? 3 9s. Another red? 2 8s. And then green? 2 7s. But, is that the only order you can get 2 reds and 1 green?
3.
So multiply by 3, right? So you can think of it as the green one could have been here, here, or there, right? That's 3 cases. Or, how many 3-letter words can you form with 2 R's and 1 G? That's like Mississippi, right? It would be 3 factorial, but since there's 2 R's over 2 factorial, you get 3. Anyway, this is the key. You gotta have that multiplication factor there. So these 4 problems I did without replacement. Now let's do all 4 problems. No, we don't have to do all 4. Let's just do these here. What if I said with replacement now? How is that gonna change? I'm gonna randomly draw 3 marbles. What's the probability of getting 1 of each color with replacement? In other words, you pull it out and get it right back in. Okay, specific case. What's the probability of pulling out a blue on the first draw? 4 9s. Throw the marble back in. What's the probability now of getting a red? And then now green. And do I need to multiply by that 3 factorial? Yes, because is that the only way I can get 1 of each color? No. So there's 6 orders that can be put in. So you need to multiply by the 6. Okay, what about this? What's the probability of pulling out a red on the first draw?
2 9.
Put it back in the jar.
3 9.
Back in the jar.
2.
2 9s. And what do I multiply by?
3.
3. There you go. It's pretty easy, huh? Hey, by the way, next week during Extended, we're going to be filming this class now.
Why?
We're going to be filming, actual filming. Like, I'm not sure how I'm going to do it. Like, in another class, I was experimenting by holding the camera here. I don't know what's going to happen, but we're going to film.
Yeah.
But why?
Because I have to for a project. So it's gonna be the same as, we're gonna redo the parametric equation lecture. That's what we're gonna do. Because the project was on parametric equations. I actually filmed it on that, but it wasn't good enough, so we're gonna have to do it again. We'll do it during Extended. So instead of watching Flatland, we're gonna do that.
Wait.
But don't worry!
Wait, do we have to pay attention if we already learned the lecture?
Yes!
But you said we already learned it.
You're gonna yeah, but does that even matter? You guys forgot everything. And you need your iPad and your graphing calculator, because I'm gonna call on people to graph it on either your TI, your what's the other thing called?
Pocket
A Prism or a Pocket Cast. We're gonna divide it into like 3 groups. And that's why I have the camera here, because then I'm gonna have to come.
Wait, is that next week or the week after?
No, next week is Extended. So you're just gonna have to forego Flatland.
It's 2 weeks.
Yeah, that was 2 weeks.
Okay, 2 weeks then. Whatever it is, that's when it's gonna be. Okay, last thing is the birthday problem. Now, if you were in my summer school class, we did the birthday problem, yeah? You guys remember?
No
something about
overlapping
that?
birthdays. Oh no.
Okay, now make sure you understand this. Every year we go through the same thing. Yeah, we understand it, and then on the test, fatal error. Okay, this problem is going to be on the quiz and the test.
With certainty.
Yes, the probability is 1. It'll be both on the quiz and the test. Okay, how many different birthdays are there from January 1st to December 31st?
366.
366, because it is possible to be born on February 29th, right? In fact, we had one person born February 29th, Sarah Zhang. That's really her name. However, the probability of being born on February 29th is not the same as the other days. So we're just going to pretend like it doesn't exist. So Zhang does not exist. Okay, so for the sake of, just for simplicity, there's only 365 different birthdays, okay? This is just for simplicity. Okay, so this is like a problem you're going to see on the SAT. I have a room, I'm going to have a party. How many people do I need to have at this party to be 100% sure at least 2 people will have the same birthday?
366.
Exactly. 366. You guys understand that? That's like elementary school, right? Because look, there's 365 different birthdays. If I have 365 people at a party, isn't it possible that everybody could have different birthdays?
Yes.
It's possible, it's not probable, but it's possible. And if that happens, once one more person enters the party, guaranteed it's got to match up with somebody, because there's only 365, right? Okay, so that's easy, that's elementary school, but now, okay, now pre-calculus. How many people do I need to have at this party to be 50% sure at least 2 people will have the same birthday?
23.
Oh, you guys remember from somewhere. How did you guys remember that?
Oh, I watched a video. It's the amount of people on a soccer field. Or a football field or something.
What?
It's 11 people on both teams and then the referee.
There's only one referee? I thought there's like 3.
On the field, The other guy's on the field.
There's a video about that?
Yeah.
Where?
It's number file or something.
What?
Number file on YouTube.
You said it.
Number file.
Yeah, like the love of numbers.
Oh, well, file. Like pedophile.
Yeah.
Good one, love. So a lot of people think, oh, 366 people to be 100% sure, so 50% sure, you need 183 people. No, that's enumerate. You're enumerate if you think that. It is not, and that's because that's not how probability works. So I'm going to show you how to do this birthday problem. Now make sure you understand this because it's on the next quiz and test. So, one person comes to this party. What's the probability that he has a birthday?
100%.
Guarantee he has it, 1, right? But instead of writing 1, I'm going to write 365 over 365 because there's a pattern. Period 3, it took a while for them to see the pattern. But you guys are period 6, so hopefully you can see it quickly. Second person comes to the party. What is the probability that this person's birthday is different from that person's birthday?
64.
364 over 365. Everybody agree? Because this person has one of the 365 birthdays. There's only 364 other ones, right? Now, if I multiply these two numbers together, what is the meaning of that?
It's not the same.
This is the probability that,
They're not the same.
yeah, these two people have different birthdays.
You have to minus from 1. No. Yeah.
Okay. Third person comes to the party. What's the probability that this person's birthday is different from the first two people? 363 over 365. If I multiply these three numbers, that is the probability that these three people have different birthdays. Are you starting to see a pattern? Fourth person comes to the party. What's the probability that his birthday is different from the first three? 362. Do you guys see the pattern yet?
Yes.
Okay, good, because I have to go all the way to here for period 3. It goes down by 1. So if I multiply these four numbers, this is the probability that all 4 of these people have different birthdays. So what would happen if I subtract it from 1?
And you have your answer.
Then you get the complement. What's the complement of all 4 of these people have different birthdays?
No. At least 2.
All 4 of them have the same birthday.
No.
That's what period 3 said.
At least 2.
Okay, just think of it this way. What if somebody said, all 4 of these people have different birthdays? What would it take to prove that person wrong? You have to show that they all have the same birthday. No, at least 2 of them have the same birthday. So, this is the probability that all birthdays are different. If you subtract it from 1, you get the complement. That's the probability that at least 2 people have the same birthday. Okay, somebody compute this on your calculator or iPad or whatever. Hey, somebody in period 4, they could draw it in, they do this with their hand. 1 minus this, and the thing changes it and computes it. What is it called? My script calculator. And that's pretty neat. Or you can just stare at the board like you're doing now. And maybe the answer will magically appear. I think it was faster to just punch it in on the calculator. Whatever.
Probably is.
We're not going anywhere until we compute it. You guys better not act like this when we film.
Well, how come you're not going to film the other class?
We are. I'm going to film all 3 and we're going to pick the best one. So that means period 3 out already. Because they don't even say anything. They just sit there like this.
0.0027.
And once in a while, Hana Olga moves a little bit. That's about it. The rest of them are like statues. And even by bringing Sito in, at least the enthusiasm is raised a little bit, but it's kind of the same. So what is it? Tag?
0.00273.
0.0027. Really?
I think that's 0.01.
Oh, I don't know.
1.016.
0.016.
0.016.
0.016. So 1.6% then.
Yeah.
Okay, we got 2 different answers. Who's going to break the tie? Okay. So, if you have 4 people at a party, randomly selected, the probability that at least 2 of them will have the same birthday is 1.6%. That's not very impressive, yeah?
Yeah.
Now, if you were to continue this, like what if a 5th person comes to the party? Then it's going to be this, right? Because you guys see the pattern, right? 6, 7, 8. Well, as it turns out, we're not going to do this because it takes too long. If you had 23 of these, that's the first time the probability will go over 50%. So you only need 23 people in a room, randomly selected, and the probability is going to be 50%, at least 2 people will have the same birthday. That's like a coin flip. But see, the thing is, you wouldn't bet a lot of money on a coin flip, right? I'll bet you $100 it comes up heads. So what about 90%? How many people do you need at a party to be 90% sure at least 2 people have the same birthday? Takaki?
50.
No, 41. And then what? And summer school. I told you guys this. What about 99%?
57.
You need 57. Well, actually, it's 58. 58 people in a room. The probability is 99%. Because a lot of people would think, oh, you got to take 99% of that. That's 360 something. No, you only need 58 people at a party. 99%. At least 2 people are going to have the same birthday. Isn't that like almost guaranteed? Isn't that? What did you say? 99% is almost guaranteed. Like, what if somebody said, okay, the parachute opens 99% of the time. What did you jump?
Yes. Yes. Yeah. It's fun.
Or do you need 99.9%?
No. You don't need it.
99 is good enough.
Yeah. This means one person gets my birthday.
Okay, so what we did in the other classes is we wrote our birthdays. And look, we only had 28 people so far. And so if you had 28 people, 50-something%.
Oh.
But what would it take for you to bet money? 90%? 90% is a good bet.
50% I would bet.
Are you serious? You should just go to Vegas then. Okay, so we already got a match. Where was the match?
January 11th.
Yeah. Anyway, there's so many January birthdays. What happened? Was there a power outage like in April or May or something? What the heck happened? I don't know. Okay, well, let's just keep on going. Anyway, if you just look at this list, I bet you some of you already see people you know that have that birthday, I bet. Huh?
Spencer Kim, May 10th.
No, he's in this class.
Oh.
Okay, start with Dai.
Yeah.
Just tell me, like, if your birthday is March 1st, just go 3, 1. Dai.
19.
What?
9, 19.
Oh, we got a match! Whoa! No, but see, everybody thinks, oh my gosh, that's incredible. No, it's not incredible. It's supposed to happen. See, that's the difference between being numerate and enumerate. That's supposed to happen.
Who's the other person?
I don't know who that was. Oh? Okay, continue. Sito.
7, 7.
8, 8.
6, 12.
And 9.
5, 17.
12, 28. Oh, 11, 5.
12, 23.
Oh.
7, 12.
7, 27.
Oh.
6, 21.
420.
8, 25.
Is that Hillary's birthday?
Yeah. It is?
12, 11.
8, 17.
4, 6.
9:15.
What about you, Mr. Park?
That's me right there. So we only got 2 matches. I thought we would get more. So if you add, how many people in this class? 3, 8, 13, 22, 24. You add 24, so n equals 52. So the probability should be 90-something%. And we got 2 matches. Anyway, I went to a conference one time. It was in a school cafeteria. I don't know what kind of conference it was. But they had this icebreaker. So they said, okay, I want you to line up from January 1st to December 31st over there. I think there was like 60-something people there. And so you're supposed to talk to the other people, right, and tell them, when are you born? And then, so you line up. And then what happened is, there was like 5 or 6 pairs of people that had the same birthday. In fact, there was one group had 3 people on the same birthday. And everybody's going, oh my God, that's incredible. And I was just laughing. It's supposed to happen. More than 50, that's better than 99%. At least 2 people are going to have the same birthday. So at the end, you know when you have to evaluate the conference? You guys ever been there? So I explained to them, when you have 58 people, the probability is 99%. At least 2 people have the same birthday. I don't know what happened. They probably just do it. They still think all the stars was aligning and things like that. No, it's supposed to happen. So that's why, see, people who know numbers can prey on the enumerate. So you go to a party, you scope it out, you get 50-something people here. You're talking to somebody, hey, I bet you $20, I bet you $50, at least 2 people have the same birthday. Right? And then 99% of the time you're going to win. Right? I mean, there is a chance that you could lose, right? Very small chance. But if you lose, then you just go to another party. No, because if you go to 100 parties, probably you're going to win 99 times and lose once. Probably. This is all probability, yeah? But think about it. If you won 99 times, you won 99 $20 bills, and then you just lost once, you still made a bunch of money, right? Yes! You got to prey on the enumerate. That's what people do. That's how they make money. What time is it? Did you ever, okay, what if, okay, you're at home, and you're getting your mail, and then you get this mail from somebody who says, oh, this stock is going to go up tomorrow. And then you look at, then you follow it, you look in the newspaper, hey, it went up. The next day you get another letter, it says, hey, that same stock is going to go up again. And then you check, hey, it went up again. And then you get another letter the next day, it says, okay, it's going to go down. And then you look at it, it went down. And then the 4th day, it says, it's going to go up. When you look in the paper, it went up. And the 5th time says, okay, if you want to know what the next one, just send $1,000 to me and I'll tell you what it is. What is that? Is that good enough? How many times does the guy have to be right before you would invest money?
58.
Huh?
58.
50 times he has to be right.
9 times.
What? That even making sense. No, but that's how people prey on the enumerate. Think about this. If, okay, let's say you send out a million letters. Million letters. What's a million? Half of them say it's going to go up. Half of them say it's going to go down. Right? And the ones, okay, one of these is going to be right. Okay, let's say that one's wrong. So out of these, you send half. So 250,000, you send 250 letters that say up and 250,000 that say down. That's not, is that 250,000? No. Okay, so let's say this one is wrong. So out of these 250,000 people, you mail out 125,000 that says going up, 125,000 going down. And you just keep on going. So let's say this one is wrong. 60, 2, 5, 0, 0. So you send out this many letters, half of them going up, half of them going. And so after a while, like, right? And you get it down there, the people are going to see, oh, this person got it right like 8 times in a row. I think I want to invest with this guy. But he's just playing the numbers right there, right? You know what I'm talking about? No. Okay, just make sure you understand this birthday problem. So you're going to get one problem on the homework tonight. It's going to be on the quiz and it's going to be on the test. Yeah.
Calculator.
No. No, I'm not going to use days of the year because that's too big. So like if you look at tonight's homework, I think it's days of the week. So you would start with 7 out of 7. And then I think on the quiz I use months. So 12 out of 12. I'm just telling you everything, yeah. And then on the test I'll say there's a certain planet with only like 16 days in a year. So then you start with 16 over 16, right?
Why does it have to be a circular?
Why does it have to be what? Okay. Done. Okay, if this video is any better, then we'll put it up if I can figure out how to put it up.